Hello, I would like to present our recent works on hybrid 3D representations for 3D understanding. Every field is defined by core problems. Take the field of 3D vision, for example, where the primary goal is to recover the underlying 3D structures from RGB and RGBD images. Core problems included pose estimation, structure from motion, and multi-view stereo. Thanks to the availability of big data for both 3D models like 3D Warehouse UB3D and 3D things such as SunCG and ScanNet, the field of 3D vision has undergone various shifts of research focus. For example, from 3D reconstruction towards using 3D data as a modality for visual understanding. Core problems include classification, segmentation, and object detection. It is, though, interesting to compare 3D vision and 2D vision. In fact, both fields study almost the same set of problems, such as classification, segmentation, and detection. One way to differentiate them is to look at how data is represented. In fact, we always have to turn input and output into their vectorized form for a particular problem, and between them we can then apply various machine learning algorithms. Although the representation issue is relatively clear for 2D images, which it has a natural vectorized form as an image grid, it becomes less clear for 3D models. In fact, for a single 3D model, there exist many possible representations such as volumetric implicit representation, triangular mesh, point cloud, multi-view representation, and high-level representations such as SIGGRAPH and semantic segments. None of them is universal for all the tasks, but all of them have benefits in certain tasks. The notion of representation is also important for encoding the output. Consider the task of object detection. Recent techniques have shown the potential of regressing box parameters, yet there are many possible ways to encode a box, such as centers and sides, face centers, and edge centers. The theme of this talk is to consider hybrid representations that combine multiple single representations. I will divide the talk into two parts. In the first part, I will discuss how this view is beneficial under the supervised learning setting. We will go through basic tasks in pose estimation, relative pose estimation, and object detection to get a flavor on how this can possibly be done. Then we will provide some analysis to understand the benefits of hybrid representations in a more principled manner. In the second part, I will discuss how to leverage both unlabeled and labeled data for network training under a graph of hybrid representations. Okay, let's start with the supervised learning setting. Before going into the technical details, I would like to emphasize a little bit about the history of hybrid representation. In fact, you may wonder that where does hybrid representation come from? It originates in computer graphics and computer-aided design, right? Hybrid representation is widely used in the so-called CAD systems. So in graphics, for example, if we want to do collision detection of of models that are represented as triangular meshes, you have to use a spatial data structure to accelerate the computation. The hybrid representation have been used in for example, in field simulation and so on. But the focus of this talk is using hybrid representations for recognition, for understanding. That separates this line of works from the existing literature. The first topic I will cover is extreme relative pose estimation. The task is that we are given two partial scans, RGBD, as shown here, of the same underlying environment. Our goal is to estimate the relative camera pose between them that is characterized by rotation and translation. This task is important across many settings, such as multi-view structural motion, reconstruction from depth scans, reassembling fractured surfaces, and various SLAM settings. A typical pipeline is to extract features from both input scans, build correspondences between them, and feed the widget transform to a consistent subset of feature correspondences. In the deep learning era, this pipeline has been replaced by a neural network that consists of feature extraction towers for descriptive computational feature extraction and correlation modules for matching extracted features. Nevertheless, most existing works only consider the setting where the two input scans significantly overlap with each other, so that we can extract shared features to match. They are not applicable to the setting where the input scans have small overlaps, as shown here, or do not overlap with each other. This small overlap and non-overlap setting, however, enjoys many practical applications, such as early detection of loop closure, reconstruction from a few snapshots, and solving jigsaw puzzles. This slide shows the key idea of our approach for matching non-overlapping or small overlapping RGBD scans. We call it extreme relative pose estimation. Motivated from recent advances on using neural networks to perform scan and sync completion, our approach takes the two input scans and perform sync completion to recover the underlying complete 3D scenes. This completion step turns the non-overlapping scan matching problem into the overlapping scan matching problem. Essentially, we then extract features from the completed scans and perform relative pose estimation. The critical task here is to determine a suitable intermediate representation for scan completion. One possibility is to consider the cube map representation, which we used in the CVPR paper last year. However, this representation works less well among visions that are far away from the visible visions due to the limitations in the image-based representations. Our key idea for completion is to consider multiple intermediate representations, including the cube map representation, which works well for points that are close to the visible vision, and two other representations such as 2D top view and planar structures of the input scene. It turns out that these two latter representations provide complementary features to the cube map representation, particularly among visions that are far away from the visible visions. Given the completed intermediate representations, post-regression picks features from those completions and performs spectral matching on local features. Optionally, we also perform local refinements with learned geometric constraints in this year's CVPR paper. This approach essentially enforces geometric constraints to select consistent correspondences. In other words, this step automatically selects best features under each individual representations that are consistent with each other. We also show how to perform end-to-end training of the hyperparameters of the post-regression module and the completion networks. right? Please refer to the paper for more details. We perform experimental evaluation across 3 datasets: SunCG, Matterport, and ScanNet. ScanNet contains real scans. We divide scan pairs into 2 groups, namely overlapping scans and non-overlapping scans. Experimental evaluation considers both angular error for the rotation and absolute translation error. This table shows quantitative results on 3 benchmark datasets. Our approach significantly outperforms non-learning-based approaches. Since those approaches only apply in the overlap setting, we basically compare them on those subset of scan pairs. The performance gain indicates that even for the overlapping scans, performed scan completion is valuable, right? Since it provides useful features to match. Compared to using a single representation, using multiple representations, this further reduces the rotation and translation errors. Okay, that is the end of the first paper. Now I'm going to talk about the second topic, where we study 60 object pose estimation, which is a core problem in 3D vision. So the task of 60 pose estimation is the follows. Suppose we are given an image of an object where we know the ground truth 3D model. Our goal is to predict the 60 pose, right, characterized by the rotation and translation of this image object from the coordinate system associated with that object. This problem has been studied extensively in the literature. There are many possible solutions. A popular pipeline is to first predict intermediate representations such as the key points, from which we then regress object poses. A key advantage of this framework is that key points allows us to instill intermediate supervision rather than basically pose labels. Another advantage is that the post-regression step leverages geometric constraints, right, which are unavailable in black box end-to-end neural networks. Similar to using hybrid representations for scan completions, our idea for 60 object pose estimation is to consider multiple intermediate representations. Besides key points, we consider edge vectors, namely edges between key points, and symmetry correspondences, namely correspondences that encode underlying reflection symmetry. Advantages of these additional representations include each intermediate representation tends to know different features. Okay, in fact, the features that are suitable for building correspondences are clearly different from the representations that are used to locate individual feature points. But on the other hand, all those intermediate representations provide meaningful constraints on the underlying pose. So this slide shows the neural network architecture, right? Given the input image, we use the PVNet as the backbone network architecture. We modify it to offer predictions under 3 intermediate representations. Note that the network parameters are largely shared, except for small branches for predicting different representations. So in other words, the overall overhead is still very low. Given the predictions, we perform post-regression by combining an initial post module and a post-refinement module. This slide shows the details of the post module. Essentially, we penalize the geometric constraints induced under each prediction using a robust norm. The initial pulses are given by ePMP, and we perform Gauss-Newton optimization for refinement. Okay, so given the intermediate representations, we can write out the constraints. The rest are quite common procedures for post-regression. So here I just want to show one result on non-model occlusion, which is a very challenging data set. And using hybrid representations, right, we can reduce both the translation and rotation errors. Okay, and more details can be found in the paper. So this is a 1-minute video of our.
We introduce hybrid pose, a novel 6D pose estimation method using hybrid representations. Given a 3D model and an RGB image, we would like to find a rotation matrix R and a translation vector T that transform the model from its object coordinate system to the world coordinate system. Hybrid pose utilizes a convolutional neural network, which takes the RGB image as input and predicts 3 different types of intermediate representations, including key points, edge vectors, and symmetry correspondences. The pose regressor receives predicted intermediate representations as input and formulates pose estimation as an optimization problem. It estimates the rigid pose parameters that best align 2D and 3D intermediate representations. For more details, including our open source implementation, search hybrid pose on GitHub. Leave a star if you like our work, and create a GitHub issue if you want to discuss anything with us.
Okay, so this is the second talk, which is 60 object pose estimation. Now let me move to the third tab.
We introduce
The third topic I would like to talk about is 3D object detection using hybrid geometric primitives. So the paper is on arXiv, and the code has been released. So the task is that given a 3D point cloud of a scene, our goal is to detect object bounding boxes from objects in this scene. Object detection is one of the most important visual recognition tasks, and there are many approaches in the literature. Our approach is motivated from recent works that formulate object detection as a regression problem. This includes the works in the 2D domain and works in the 3D domain, right? Regression, box parameters. So of course, to regress box parameters, it depends on how we encode the box. One approach which was used in a recent landmark result VoltNet by Qi et al. Is to encode a 3D object bounding box as a center plus the size and orientation. A downside of this encoding is that whenever the prediction for one of the parameters is wrong, the entire the location of the box is wrong, right? So our idea here, instead of using just a minimal set of parameters, is to consider our complete set of box primitives, including object center, 6 face centers, and 12 edge centers. In total, there are 19 geometric primitives. They provide our complete set of constraints for one box, and because they are our complete, we can tolerate wrong predictions in these geometric primitives, for example, using robust regression, which we will talk about later. Okay. So besides providing a complete set of constraints, so these representations or geometric primitives are also beneficial to each other in terms of learning feature patterns. For example, the box center, which is mostly suitable for solid objects. In contrast, face centers and edge centers are suitable for objects with distinctive faces and edge features, like a table shown here. So given this view, this slide shows the overall network architecture, which consists of three modules, including a module for generating primitives, a module for fitting initial object proposals to the primitives, and a refinement module, okay, which essentially leverages the features associated with hybrid geometric primitives. So the geometric primitive module follows that of the WolfNet, but we enhance the feature extraction tower to provide features for different geometric primitives. Given this our complete set of primitives, the initial object proposal module essentially feeds object proposals to these geometric primitives using a robust norm, right? Essentially, we use the truncated L2 norm to match each object proposal to the set of most compatible geometric primitives. Okay, this solves the optimization problem, and because of that, the backpropagation is also easy, right, through the implicit function theorem. Okay, and using the robust norm can certainly tolerate wrong predictions, right? They do not really affect the box parameters. Okay. Given the initial object proposals, for each object proposal, we aggregate information associated with the matching geometric primitives, meaning that those are close to the corresponding geometric primitives for each object proposal, and we pass through a neural network to refine that, right? So essentially, those features which are passed through the entire thing contains a contextual information, and this module aggregates those such contextual information for proposal refinement. Now we want to show some experimental results, which are also very encouraging, right? So on ScanNet v2, we improved from the state of the art by 85% in terms of MAP score with respect to the hyperparameter 0.25. And in terms of the hyperparameter of 0.5, the improvements around 15%, meaning that our approach is quite accurate in terms of detecting those objects that are salient objects in the scene. Okay. So we also have noticeable improvement on some RGBD v1. The improvements are also consistent across all the categories. In particular, the categories where existing methods perform poorly, our improvements are quite salient by more than 10%. Okay, so this is with respect to MAP 0.25. So far, we have given 3 concrete examples where hybrid 3D representations, both for the input, for the intermediate, and for the output, okay, are beneficial for respective tasks. So here we want to give a little bit more insight into why hybrid 3D representations are useful and in practice. Okay, so one argument is that the predictions on the different representations are not strongly correlated. Okay, so we can understand this from the perspective of our parameterized networks. There are exciting advances in this on this topic. So basically what people have shown that in an over-parameterized regime, the optimal network parameters are close to the initial network parameters, right? So meaning that when you initialize the network parameters with them randomly, because there's just so many parameters, you don't need to change the network parameters a lot in order to feed the data and also generalize as well. There are many very exciting papers on this topic very recently. Okay, so what does this mean is that therefore, because the optimal network parameters are close to the initial network parameters, if the network parameters on the different representations are initialized independently, okay, this also applies to, for example, in the hybrid approach setting, we share the first few layers, right? So unless the parameters of different branches initialized independently, then the resulting network parameters are not strongly correlated, right? Because they're close to the initial ones, okay? Does this actually apply in practice? So empirically, we also justify this claim on real data. For example, for the task of 3D object detection, we show the covariance matrices of the predicted geometric primitives on ScanNet and some RGBD. We can see that both the covariance matrices are well approximated by diagonal matrices, meaning that the predictions somehow uncorrelated with each other. So this is each prediction also has a bias. The second argument is that the bias is smaller than the variance. Okay. Empirically, these two plots show the results on the left is ScanNet and right is some RGBD. The blue bars are bias and the orange bars are variance square root. Okay, you can see that the bias is generally smaller than the variance. Now we proceed to analyze the output prediction that is derived from intermediate predictions. Let us begin with a simple regression problem where we want to feed the output x to a set of intermediate representations yi. We assume that y are independent random variables, and they satisfy that the variance is significantly larger than the bias. It is clear that the optimal solution is simply the average among the yi's, and x star satisfies that the bias remains similar, though that this is in the worst case. Okay, but the variance is significantly reduced. Okay, the analysis is quite straightforward. We can consider a general setting where the output is given by solving nonlinear least squares. And this setting applies to both hybrid pulse for 60 pulse estimation and H3D-net for 3D object detection. In this case, we can consider the local approximation of the optimal solution, which is a linear transform of the intermediate predictions yi. And we can have similar arguments that the bias remains similar, and we have a reduction on the covariance matrix. Yet in this general setting, characteristics of the variance reduction depend on the configuration among different representations. So let's look at the concrete example under the 60 object pulse estimation application. We have considered a specific configuration where the object is a box in front of the camera. The size of this box is 1 times 1 times delta. It has 8 key points, and symmetry correspondences are given by the front face, which is perpendicular to the viewing direction, the z-axis, in this setting. In this case, we can approximate the covariance matrix as follows, where lambda mu's are turn rates, and where sigma k, sigma e, and sigma s are variance of key point predictions, H vector predictions, and symmetry correspondence predictions. The H matrices dictate the configuration specified by the constraints between the individual predictions and the underlying pose. We can see that H matrices of edges and symmetry correspondences contribute to the certain 6 elements, which correspond to the translation and rotation of the z-axis, right? Which is the viewing direction in this case. So in other words, edge vectors and symmetry correspondences help reduce the variance along the viewing direction for both translation and rotation. And this explains why hybrid approach works remarkably well on non-model occlusion, because the intermediate prediction is quite noisy. A couple of further comments. So what we have seen so far include intermediate predictions mostly uncorrelated, and in particular for each prediction, the bias is usually smaller than the variance. Okay, when combining multiple networks for a single task, there are generally 2 options. One is we stick to a single representation and we use multiple networks, right? So the ensampling idea. And in this case, we can imagine that we will have variance reduction because of the predictions are mostly uncorrelated. But the bias reduction is less effective, right? You can imagine that the bias on the different networks turns out to be similar. Okay, not exactly the same, but tend to be similar. Another option, what we have been applying, is called multiple representations and a single network per representation, right? So in this case, we can get potentially salient variance reduction. This has been justified in the hybrid approach case. And we argue that the potentially bias reduction, right? So maybe on the different representation, the bias can have the so-called concentration effects. Okay, all of these require further theoretical justification. So far, we have considered a hybrid 3D representation under the supervised setting, where we have labeled data. So now we move to the second part of the talk, where we consider both labeled data and unlabeled data under the hybrid 3D representations. So again, here we are looking at a broader view of this kind of semi-supervised learning. So we have hybrid representations. We want to organize them. The idea is that we want to organize them using a graph, where the graph nodes are individual representations and edges are either deterministic procedures or neural networks that convert one representation into another. I will walk you through 2 advantages on why such graphical hybrid representation is useful. The first advantage is that it can leverage more training data. Okay. So here we want to have a toy example. Suppose we have 2 languages that possess very limited data for the task of machine translation, right? So when you translate one language into another, to train a neural network, we need sufficient training data. So instead of just looking at those 2 languages, we can address this issue by introducing a model language which has rich paired data with the first 2 languages. Right, note that the rich paired data you cannot really compose. Right? For example, a sentence in Korean has a translation in English, but that particular sentence may not have a translation in Portuguese. Okay, but on the other hand, you can train 2 neural networks to do the machine translation. Okay, between the model language and these two original languages. And in this case, you can compose these 2 networks to obtain a machine translation between the first 2 original languages. Okay. So another advantage is that it leverages unlabeled data, which is very interesting here. So here again, we want to give a very toy example, right? So say we have one input and one output, and we want to train a neural network that maps the input to the output. So there's a standard setting where we're just using a single vectorized representation for the input, then we train a neural network. But in this case, we can only use labeled data, right? Because we need to provide constraints on the neural network training. So that is not interesting. So what is interesting is that you can consider multiple representations of the input, right? So in this case, we can have 2 neural networks that maps each representation to the output. So in this case, we can use unlabeled data. For example, when you have some unlabeled data as input, right, because there are two paths between the input and output, we can have two outputs from this unlabeled data, right? Even though we don't know the label, but we can ensure that, enforce that the predictions somehow compatible with each other, right? So this is an unlabeled training loss. Okay, so in the following, I want to show a very recent work called Path-invariant map networks, CVPR last year. Essentially how to generalize this idea to general neural networks, or a graph of neural networks. Okay. So again, we go back to the language example. So here we have three languages, three neural networks. Abstractly, we can summarize this using a directed graph with three nodes, and each of which represents a language, and three edges, each of which represents a machine translation network, right? And in this case, what we are doing here, for example, we have F3 is the one that corresponds to the network with insufficient labeled data, right? So F1 and F2 are the ones that with sufficient labeled data. So the previous example essentially can be just summarized using one equation, right? Essentially says that F3 is identical to the composition of F2 and F1, right? So we call this path-invariance, meaning that the composite neural network from the top to the bottom is independent of the paths, right? There are two of them, right? We choose. So I want to say that this is somehow slightly different from the cycle consistency argument, which involves a cycle of neural network, right? So in that setting, essentially says that the composition should be identity, okay? So there's a distinguish between them, right? Meaning that the path-invariance does not equal to cycle consistency. Which later we'll see that from the algorithm perspective, they're also quite different, okay? In terms of enforcing, deriving the self-supervision constraints on general graphs. So formally speaking, if we have more general graphs, we want to define the path-invariance constraints as the fact that the composite maps allow all the paths that between two identical nodes are equivalent, right? So we can form, this is very easy to state. And so this is easy to say, but what is interesting here is that you don't really want to enforce the path pairs, right? So among all the path pairs, right? So can we actually instead choose a small subset of path pairs? We call it the path-invariant basis. That when you enforce the path-invariant constraints on those path pairs, it induces path-invariant property of the entire graph. Okay, we will talk about this in a moment. But suppose we have the path-invariant basis, namely a small collection of path pairs, right? So we can effectively formulate the problem of joint learning of neural networks. The objective function essentially combines a supervised loss and unsupervised loss. Okay, so the supervised loss enforces the neural networks agree with the training data along a subset of edges, right? In the language example, we have two edges that we can impose supervised loss, okay, sufficient training data. The unsupervised loss enforces the invariance property among path pairs in the path-invariant basis, right? So in the language example, we have one such constraint, right? So this involves unlabeled data. Okay, now we go back to define the path-invariant basis, right? So the critical task here is to define what really the induction means, right? So here we summarize three primitive operations, right? Those are the operations, simple ones, right? So merge, stitch, and cut. Okay, cut is very special for directed graphs, right? So those are the three primitive operations where the path-invariance property is preserved. Okay, and there are three operations that preserve the path-invariance property. Okay, So that is induction operation, right? So meaning induction, meaning that you can combine a subset of those operations in some order to go from a collection of path pairs to a path pair. Okay, so that is our assumption. Under this assumption, our main result here is that we can show that for arbitrary directed graph with n vertices, m edges, there exists a path-invariant basis with size at most n times m. Okay, n is the number of vertices, m is the number of edges. Okay, meaning that it's a polynomial size. And the proof is not that trivial, and you can read the paper. So essentially, the key insight here is that a directed graph is a cyclic graph, that DAG, of strongly connected component. Okay, so we build on top of that to derive the path-invariant pair, right? So for the DAG, we can use a vertex order to construct a path-invariant basis for DAG. Okay. So this also gives us also algorithm for computing path-invariant basis. Okay, the details can be found in the paper. So I also want to draw some connections between the path-invariant basis and with another combinatorial or algebraic quantity and graphs called cycle basis, right? So cycle basis essentially is a collection of cycles that can induce other cycles through linear combinations of vectorized encodings, right? The edge indicators of cycles. And depending on the combination coefficients, cycle bases fall into different groups. Okay. So we can extend the cycle basis to cycle consistency basis, right? Which are defined on directed graphs. The operations are merge and stitch. So in a recent NeuriPS paper, we studied this in depth. So the difference between the path-invariant basis and cycle consistent basis is as follows, right? So for the cycle consistent basis on directed graphs, we know the minimal size. Okay, so it's number of edges minus number of vertices plus 1 is related to the spanning tree, okay, of a graph. But on the other hand, for path-invariant basis, right? So there's a conjecture which stated in CVPR paper saying that computing the minimal path-invariance basis of given graph can be hard, right? But on the other hand, we do have a polynomial time algorithm for computing a path-invariant basis of a polynomial size. Okay, so there's another conjecture. Essentially says that testing, right? So testing is also very difficult, right? Given a collection of cycles or path pairs, we conjecture that the testing the cycle consistent basis, path-invariant basis also be hard. Okay, so both conjectures are interesting topics for future research. All right, you may want to argue why not just randomly sample path pairs, right? Which is inspired from the success of stochastic gradient descent for training neural networks. In fact, there are 3 advantages of pre-computing a set of path pairs. The first one is that unless for special graphs, one may need to sample many, sometimes exponentially number of path pairs to ensure the path-invariant property. Okay, sometimes you have to sample many non-path pairs. Okay, this is ineffective. Also, there's a cost of implementing one path pair overhead. Okay, the data structure-wise. From the optimization perspective, right? So if you have a non-path pairs, the algorithm converges very slow. Okay, converges very slow. Okay. All right. Does it work in practice? So we provide 2 set of experiments here. The first experiment is on semantic segmentation under hybrid representation. Now let me formally introduce this graph, right? So this is a graph with 7 representations, 1 input, 1 output, which is output semantic segmentation. And we have 3 point cloud representations and 2 volumetric representations. Okay, so the point cloud representation point clouds at different resolutions, and so do the volumetric representations. The insight here is that even under the same geometric representation at different resolutions, the neural networks tend to learn different features. Okay, and we also have networks between different representations, right? So essentially, for example, for the semantic segmentation task, what are the points on the to select in order to maximize the performance of the output? Okay, so under this graph, it applied our framework on the ScanNet semantic segmentation benchmark, and the message is summarized here. So we can use 8% of labeled data plus 92% unlabeled data to achieve the performance of using 30% of labeled data, right? So this is true for either using one neural network for training or using a sample of them. Okay, so the results are quite consistent. So we also tested this on the standard benchmark for computing dense correspondences between geometric objects. So the state of the art has been using no-rank matrix recovery techniques. So here we show that for various sparse graphs, this kind of enforcing the consistency along or invariance along past pairs has the advantage over convex or non-convex relaxation techniques. I should mention that there are many relevant works on leveraging the joint learning of tasks of neural networks to boost the performance of network training. However, in our case, we focus on how to formulate self-supervision constraints on general graph of neural networks. Okay, so in this talk, we have covered different aspects of hybrid 3D representations, both from the supervised learning and from the semi-supervised learning that combine both labeled and unlabeled data. Okay, we talked about how to model this and discuss the algorithm for doing so. And there are many future directions. In fact, this is just at the beginning. The many open problems. For example, when choosing hybrid representations right now is pretty much hand-encoded, handcrafted. Is there a principal way to determine what representations are beneficial to each other? A relevant question is that how to construct latent representations, right? So far, all the representations are handcrafted, and can we insert latent representations, right? So and how to connect them with other representations to maximize the performance of, for example, a graph of neural networks. Another question is related to the trade-off between accuracy and complexity, right? So using hybrid representations certainly increase the network complexity. So in all the examples we have shown, right, we address this issue by sharing features, but allowing some independent decoupled variables for each individual representation. But nevertheless, there's some increase in the network complexity. On the other hand, we gain substantially in terms of accuracy if we have this both from what is the principal way to trade off between the accuracy and complexity, right? The computational framework. So this is very interesting to explore. And we need more theoretical justifications, and we are working on that, in particular understanding why hybrid representations are beneficial in the supervised setting. Okay, so I would like to acknowledge funding agencies, and I'm happy to take questions.